Welcome back to Basic Electronics. In this lecture, we will look at a series RC circuit with a single resistor, a single capacitor, and a step input voltage. It is a simple circuit and the solution is well known. We will not simply state the solution but derive it using what we already know. And when we do that, we will learn some useful ideas which would certainly help in the long run. So let's begin. We have looked at the general solution for a current or a voltage in an RC circuit with DC sources. Let us now answer this important question. Given an RC circuit, we want to find out if the capacitor voltage can change suddenly or abruptly. And we will answer this question with the help of this example here. What do we have here? We have a series RC circuit. R is 1K, C is 1 microfarad, and this RC circuit is driven by a step voltage source. Up to t equal to 0, the voltage is 0 volts, and at t equal to 0, it changes from 0 volts to 5 volts. The capacitor voltage is given to be 0 volts at t equal to 0. So Vc is 0 up to this point. And now, as a result of Vs changing from 0 volts to 5 volts, we expect this capacitor voltage to change. So this is our question. Vs changes from 0 volts at t equal to 0 minus to 5 volts at t equal to 0 plus, that is just after t equal to 0. And as a result of this change, Vc will rise. The question is, how fast can Vc change? For example, what would happen if Vc changes by 1 volt in 1 microsecond? And let us assume that this is happening at a constant rate, that is 1 volt divided by 1 microsecond, or 10 raised to 6 volts per second. Because of this dVc dt, a capacitor current will flow, which is given by I equal to C dVc dt. C is 1 microfarad and dVc dt is 10 raised to 6 volts per second. So this product turns out to be 1 ampere. With I equal to 1 ampere, let us calculate the voltage drop across this resistance now. This R is 1K or 1000 ohms, and R times I is the voltage drop. So that would be 1000 ohms times 1 ampere. So that is 1000 volts. That's a very large drop, and this would simply not be allowed by KVL. Because we have only 5 volts here, we cannot have 1000 volts over here. And therefore we conclude that Vc at t equal to 0 plus must be equal to Vc at t equal to 0 minus. If these were not equal, that would lead to a very large capacitor current, and the KVL equation would not be satisfied. So therefore, a capacitor does not allow abrupt changes in Vc if there is a finite resistance in the circuit. As long as there is a finite resistance in the circuit, which is usually the case, we must have the capacitor voltage to be continuous. Alright, now in an RL circuit, we must have continuity of the inductor current, because any abrupt change in inductor current would lead to a very large L dIL dt, that is a very large voltage across the inductor, and that again would not be allowed by KVL. So the take home point from this slide is that the capacitor voltage must be continuous and the inductor current also must be continuous, as long as there is a finite resistance in the circuit. As our first example, let us consider this simple RC series circuit. So we have R and C in series, and this combination is driven by a voltage source with a step voltage. So this Vs is 0 volts up to t equal to 0, and then it abruptly changes to V0, and it remains constant after that point. And we are interested in finding this capacitor voltage and the capacitor current as a function of time. Let us begin by writing V of t, the capacitor voltage, as A e raised to minus t by tau plus B, where A and B are constants to be determined. Now this expression, if you recall, is valid only as long as the independent sources in the circuit are constant. Now in our case, we should use this equation only for t greater than 0 because our voltage is constant only for that region. We cannot use this same equation to describe this region, for example. What is this time constant in this equation? It is simply the product of C and the Thevenin resistance as seen by the capacitor. Now this circuit is already in the Thevenin form, and RTH as seen by the capacitor is simply R. So therefore this time constant is R times C. Let us now obtain these constants A and B. And first let us look at this circuit at t equal to 0 minus. What is the situation that we have at t equal to 0 minus? The source voltage has been 0 volts for a long time, and that means that we have a steady state. The voltages and currents have settled down to some constant values. Now if this V is constant, then this current I, which is C dV dt, must be 0, and if that is the case, there is no voltage drop across this resistance, and V is then equal to Vs, and Vs is 0 at t equal to 0 minus, therefore V is also 0. So we have V at 0 minus equal to 0 volts. Now as we have seen earlier, the capacitor voltage cannot change abruptly, and therefore V at 0 plus must be the same as V at 0 minus, therefore V at 0 plus is also equal to 0 volts. Now why are we concerned about V at 0 plus? That is because this equation applies only for t greater than 0. It does not apply at 0 minus. So therefore we can use this condition to get A and B, but not this condition. Okay, let us now look at the circuit at t equal to infinity. What is the situation at t equal to infinity? We have Vs equal to V0, and sufficient time has passed to reach steady state, and therefore V and I and all other variables in the circuit would have become constant, and once again this I, which is C dV dt, would be 0 because V is a constant, and then we have no voltage drop across this resistance, and the capacitor voltage V is the same as Vs at t equal to infinity, and Vs at t equal to infinity is the same as V0, and therefore we have V at infinity equal to Vs at infinity equal to V0. So that is our second condition. We can now use these two conditions, V at 0 plus equal to 0 volts and V at infinity equal to V0, to obtain these constants A and B. So at 0 plus we have V equal to 0. So we put 0 over here. This e raised to minus t by tau is 1. So therefore we have 0 equal to A plus B, like that. At t equal to infinity, we have V equal to V0. So we put V0 over here. E raised to minus t by tau is 0 as t tends to infinity. Therefore we have V0 equal to B, like that. So our B is V0, and therefore A must be minus V0, like that. We now substitute these values for A and B back into this equation, and then that gives us the final result for V of t. So V of t is V0 times 1 minus e raised to minus t by tau. So this equation describes the charging transient. Let us now look at the discharging transient. We now have Vs going from V0 to 0 at t equal to 0, and we are interested in finding V and I as a function of time as a result of this change. Let us begin with v of t equal to a e raised to minus t by tau plus b, where a and b are constants and tau is the time constant given by R times C, because the Thevenin resistance seen by the capacitor is once again R, as in this circuit here. Now this equation is valid for t greater than 0. For t greater than 0, we have only a DC source in the circuit, namely Vs equal to 0, and therefore this equation is valid. It is not valid in this region where Vs is changing. Alright. Now, like we did in the charging transient, let us find the conditions on v of t and then calculate a and b. We need two conditions. One condition is v at 0 plus and the other condition is v at infinity. So let us first get this condition, and to do that let us look at the circuit at t equal to 0 minus. What is the situation at t equal to 0 minus? Vs has been V0 for a long time. That means all the variables in the circuit have become constants. This V has become a constant, and therefore I, which is C dV by dt, is 0 at t equal to 0 minus. If I is 0, there is no voltage drop across R, and therefore this V is the same as Vs, that is V0. So that tells us that V at 0 minus must be equal to V0. And because the capacitor voltage must be continuous, we must have V at 0 plus equal to V at 0 minus. Therefore, we get V at 0 plus equal to V0. Alright, what about t equal to infinity? At t equal to infinity, again the various quantities in the circuit would have become constants because we have steady state. Therefore, this V is a constant. I, which is C dV by dt, is 0. This voltage drop is 0, and this V is equal to Vs. Now Vs at t equal to infinity is simply 0, and therefore we have V at infinity equal to 0 volts. Now using these two conditions, we can calculate A and B. Let us see how to do that. At t equal to 0 plus, we have V0 plus equal to V0. Therefore we substitute for V, V0, and then for t, 0 here. So e raised to minus t by tau is 1 for t equal to 0. Therefore we get V0 equal to A plus B, this equation here. For t equal to infinity, we have V equal to 0. So we substitute V equal to 0 here, t equal to infinity. This term now becomes 0. So therefore we have 0 equal to B. So our constant B is 0, and therefore A is equal to V0, like that. Now putting these back over here, we get the final expression for V of t for the discharging transient. So that is V of t equal to V0 e raised to minus t by tau. At this point, it is a good idea to stop the video and derive these equations for the charging transient and the discharging transient. It is of course always possible to memorize these equations, but that is not such a good idea, because if we memorize things, they don't stay with us for a long time. They tend to evaporate after some time. Whereas if we derive the same equations, they will stay with us for a much longer time. So that is always advisable whenever possible. Let us now find the current as a function of time for t greater than 0 for the charging transient. There are two ways of doing this. One, we already know how this voltage varies with time. So what we can do is simply calculate I as C dV dt, that is C d dt of V0 times 1 minus e raised to minus t by tau. So we differentiate this entire expression. This one of course is a constant, so that drops out. Then we get C V0 by tau, that tau coming from this term here, times e raised to minus t by tau, that is V0 by R e raised to minus t by tau, because this tau is equal to R times C, and that C will cancel out and we get V0 over R here. The other way to find I of t is to start from scratch. That is, we pretend that we don't really know what v of t looks like. We begin with an expression for I of t and then find the constants involved in that expression. So let I of t be a prime e raised to minus t by tau plus b prime for t greater than 0, for which region we have DC conditions because our Vs is simply a constant equal to V0. Now we can do that because, as we have said earlier, any current or any voltage in the circuit has this form, and therefore we can write I of t like this. What is the next step? The next step is to find conditions on I of t which will enable us to find a prime and b prime. So let us do that now. As we have seen earlier, at t equal to 0 plus, the voltage across the capacitor is 0, and that tells us what the current should be. If we have Vs equal to V0 at 0 plus, V equal to 0, the voltage difference across this resistance is V0 minus 0, and therefore the current is V0 minus 0 divided by R, that is V0 by R. What about t equal to infinity? As t tends to infinity, we have steady state and all quantities including this voltage become constant, and therefore I, which is c dv by dt, becomes 0. So at t equal to infinity, we have I equal to 0. Using these conditions, we obtain these constants now. We substitute t equal to 0 here, 0 plus, I equal to V0 by R here. That gives us an equation for a prime plus b prime. Then we substitute t equal to infinity here, so this term drops out. I equal to 0 here, so that tells us that b prime must be 0. So that gives us a prime equal to V0 by R and b prime equal to 0. And finally, putting these back over here, we get I of t equal to V0 by R e raised to minus t by tau. And that of course is exactly the same as what we got in the first case. That of course is expected. Let us consider the discharging case now and find I of t for t greater than 0. There are two ways to do this again. One, we already know V of t for t greater than 0 that we calculated in the last slide. Since V of t is known, the current is given by c dv dt, so therefore I is c ddt of V0 e raised to minus t over tau. That is V of t as we obtained in the last slide. When we differentiate this quantity, we get minus cv0 by tau times e raised to minus t by tau, and since tau is equal to rc, we get minus v0 over r e raised to minus t by tau. In the second method, we start from scratch, assume some form for I of t, and then find the constants involved in that expression using conditions found for I of t. So let us do that. Let I of t be a prime e raised to minus t by tau plus b prime, and these constants a prime and b prime need to be determined using conditions on I of t. Now this expression holds for t greater than 0, for which we have DC conditions, namely the source voltage is a constant, that is 0 volts. Alright. At t equal to 0 plus, as we found in the last slide, we have V equal to V0 across the capacitor, and that gives us I at 0 plus. What is I at 0 plus? It is this voltage minus this voltage divided by R. This voltage for 0 plus is 0, this voltage is V0, so the current is 0 minus V0 divided by R, that is minus V0 over R. Next, let us consider t equal to infinity. What is the situation as t tends to infinity? We have steady state. All currents and voltages in the circuit have become constant. Therefore, this voltage has also become constant, and I, which is c dv dt, is 0. So for t equal to infinity, we have I equal to 0. Now using these two conditions, I at 0 plus equal to minus V0 over R and I at infinity equal to 0, we can obtain these constants A prime and B prime. A prime turns out to be minus V0 by R, B prime turns out to be 0, and that gives us I of t equal to minus V0 over R times e raised to minus t over tau. Let us now compare the charging and discharging transients. In particular, let us look at the currents. In the charging case, the current is given by V0 by R e raised to minus t by tau, and in the discharging case, the current is given by minus V0 by R e raised to minus t by tau. So in the charging case, this current is always positive for t greater than 0, and in the discharging case, the current is always negative for t greater than 0. And that is exactly what we would expect. If the current is positive, that means this capacitor voltage will go on increasing, and that corresponds to the charging process for the capacitor. On the other hand, when the current is negative, that is when this I is negative, the actual current is flowing in that direction, and that will decrease the capacitor voltage. So therefore, the capacitor is actually discharging. Okay, let us now look at the plots for V of t as well as I of t, both in the charging case and the discharging case. Here is the charging case. The source voltage is going from 0 volts to 5 volts at t equal to 0, and these are the expressions which we already obtained earlier for the voltage and the current. This is the capacitor voltage, and that is the current through the capacitor. So V of t is V0 1 minus e raised to minus t by tau, and I of t is plus V0 by R e raised to minus t over tau. To summarize, we have derived analytic expressions for the capacitor voltage and current for a series RC circuit when a step input voltage is applied. In the next lecture, we will look at graphs showing these quantities as a function of time. Until then, goodbye.